Hey everybody. So this is a little video just to show you how to create some nice looking figures for your paper or poster. I'm going to show you how to render in a nice way and also change the background so that it's white so that it'll actually go on a Word document, for example. All right. I'm going to use Elise's protein and ligand for this demonstration, uh, just because I picked a random one. So here we go. We got VMD going. And what I'm going to do is going to go ahead and open up this particular protein. So cool. A line drawing is not going to look very good on a poster or really anything else. So we're going to change the way that that protein looks. But first, let's do a few things to the scene. Let's get rid of the XYZ because we don't want that um, in our final rendering. So let's go to the display menu, axes, and then off. So those go away. Cool. Second thing, let's get this background white so that we can actually use these images in the appropriate locations, right? Not many black posters or black papers, right? So yeah, let's go to graphics, colors, and then in the color controls here, we're going to go to display, and then select background, and then we'll change it from black to white, which in our color picker over here is number 8. Okay, so pretty stark white here, and we can't see hydrogens anymore since they're white, but who cares about that? Because we are going to change the graphic representations. Cool. First, let's make this visible. I'm going to change the drawing method of my protein here to a new cartoon. It's a little easier to look at. Cool. All right. If you just wanted a picture of your protein, you could stop here and we could do the rendering. I'm going to just add on some features to this that will make certain parts of it stand out. For example, I've got this, change this to licorice. I've got this selection here that's going to outline the binding site of this particular enzyme here. Sorry, got distracted by an email. Cool. So what this does is shows us a nice representation of the protein while also kind of pointing out the important feature of it here. You see I've got the residues that make up the binding site in the licorice form so that we can see them easily. Cool, all right. So let's make a nice rendering of what we see here. Just get everything positioned nicely. Zoom in, don't zoom in too much or things will start to get kind of, you'll kind of get a fisheye lens effect. But yeah, you want it to fill most of the screen. Cool. All right, so how do we create our nice looking rendering? There's two things we need to do. First thing we need to do is go to the display menu, go all the way to the bottom to display settings. And let's turn on ambient occlusion. You see right here, AMB OCCL, that stands for ambient occlusion. It's a nice rendering method that shows shadows in places where there's cavities and stuff like that. It looks really nice. We're going to turn shadows off because that's just a really coarse shadowing method. Ambient occlusion does a much better job. All right, that's all we need to do. We don't have to do this, but there are certain coloring methods. Like for example, I'll select the new cartoon protein, and I'm going to change the material to one of the AO, which stands for ambient occlusion. And so these are optimized for ambient occlusion. So shiny is going to give you, as you would expect, shininess. Chalky is going to be kind of dull looking, and edgy is going to have sharper edges to make distinctions between overlapping regions. I tend to stick to chalky and shiny. Chalky I'm going to make for the protein, so it's a little more dull, and to make the binding site stand out, I'm going to change this to AO shiny. Now you don't have to use any of these materials. The typical material is perfectly fine, but the AO materials do work best with ambient occlusion. All right. So now let's actually make our figure. We go to File, Render. If we just did this right here, a snapshot, it's just going to save exactly the pixels that are on the screen here. We want something better than that. So we're going to go change our render option here to Tachyon internal in-memory rendering, not the regular Tachyon, but the internal in-memory rendering one. Cool. We also need to specify location. If you don't specify location, it's going to save into no man's land, all right? So we do need to actually be explicit about this, and yeah, I'll just put it on my desktop. I'm going to save that as a TGA file. I believe that's what it wants, but we'll see. So this rendering does take a little bit longer than other rendering methods, because what it's doing is actually firing fake photons at every graphical object within this scene. So it's actually going like, sphere by sphere, and not pixel by pixel per se, but like the ribbons, for example, in here are made up of various triangles and rectangles and that sort of thing. So yeah, it's done now because this window popped up, and let's see what our result looks like. Cool. So what you can see if we compare the two graphical representations here, we've got the live one in VMD that we can move around, right? And now we have this nice ambient occlusion one where we can actually see shadows, right? Like this loop here is casting a shadow on the arrow below it, right? And some of the places where they're more cavernous are darker, right? If we did if you use like the surf graphical representation or the quick surf, any cavity in the surface is going to be very obvious because the shadows will be cast in there very nicely. But regardless, you can see like the pixelation that exists on the edges of all of these features in live VMD do not exist here. So this looks really nice for a paper, right? Cool. Just to take it one step further, I'm going to throw some ligands in here. All right, so bear with me for a second. I'll get this up and running. Yeah, let's use a van der Waals representation for the drug itself, or in this case, the plastic. Cool. So I'm just going to use my tools. Yeah. Make this focus a little bit more. Yeah, that looks good. Maybe our ligand's a little too fat. Maybe let's put that in the CPK representation, but blow up the bond radius a little bit. Cool. I don't know. It's still blending in too much. Maybe we should use the van der Waals. Also, maybe let's make this edgy just to see how different it is. Okay. I'm just fiddling with it to get a nice view. And let's render this as test2.pga. So this is going to take a little bit longer because we have more graphical objects in here, right? We've got the ligand in here now, so the spheres are actually made up of many, many triangles. So yeah, we've added some more work for Tachyon to do, but should take about only a few seconds longer. There we go. All right, and on my desktop here, we've got test2.tga, and nice. You can see the difference in the representations here, where the junction between the spheres here is a little harder. The edges are just a little bit more stark. That's the idea. Cool. Of course, you know, obviously for your specific application, maybe you would want to have a different view to show how your ligand is fitting into the binding site or whatever, or maybe you don't even want the protein, right? And get rid of at least the big part of the protein, right? And in that way, you can get a really nice view of the binding site versus the ligand, right? Okay, cool. Hopefully this is helpful in creating your images. If you do have trouble working with the TGA file format, ImageGlass is a great Windows-based, I think maybe it's cross-platform, but it's a great image viewer that supports tons of formats. And it'll also let you save, export this, right, as a different file format, because who uses TGAs? Nobody, right? So like a ping, for example, we could resave that as test2.ping. We have that on our desktop now, and that'll drop straight into a Word document. Cool. All right. Hopefully this is helpful. If you have any questions, let me know.